So, today we are going to start a new chapter, and that is magnetic vector potential. You are familiar with potential for electrostatic field. Once you are given a charge distribution, you can calculate electric potential at a certain point because of that charge distribution, and from there you can calculate electric field. You can also directly write electric field, you have Coulomb's law type equation, but once you have potential as a function of a space point, from there also you can write electric field. We have done enough of such things in our classical electromagnetism part 1 course, but let me summarize those things, and these are all known from your school days. If you have some charge distribution somewhere, and then if you take a small charge dq here and ask what is the electric field, this electric field because of this dq, you know it is in the radially outward direction if it is positive charge, and that is 1 by 4 pi epsilon naught dq by r square in r cap direction, or you can write this as 1 over 4 pi epsilon naught. If you have origin and xyz axis, then you can write this as dq, this is a charge, and then you can write here r minus r prime vector here and r minus r prime vector here, cube of that. So, this is how the direction is taken care of. This is your r prime, and the point where you are looking for the electric field, that vector is r. So, this is the symbol that we are using. Essentially it is 1 by 4 pi epsilon naught r square is the electric field, and if you want to write potential because of this dq here, that you write as 1 by 4 pi epsilon naught, and then this dq and divided by just the distance, that is r minus r prime mod of that, just that distance. So, these are equations or so called formulas for writing electric potential and electric field, and the relation between two, is this. If you are using Cartesian coordinates, then Ex will be minus del v del x. If you are using xyz coordinates, you can write all these things in terms of xyz, and then or if you take point charge, simple, suppose just take a point charge at the origin, what is the potential here and what is the field here. So, there also you can write this kind of conditions. V will be this q divided by 4 pi epsilon naught r, and E will be q by 4 pi epsilon naught r square in r cap direction. Now, this E and this V, you can write this in terms of x y z. R is square root of x square plus y square plus z square. Okay, and similarly here this you can write as q r vector divided by 4 pi epsilon naught and then r cube here. So, once again this r can be written as x I cap plus y j cap plus z k cap, and this r can be written as this. Everything can be written in terms of x y z, and you can verify that Ex will be this, Ey will be minus del v del y, and Ez will be minus del v del z. And you can write in the combined form E is equal to this minus here, and then I cap del v del x plus j cap Ey, that is del v del y, and then plus k cap, and here it will be del v del z. Now, if you write this v outside, then it is I cap del del x plus j cap del del y plus k cap del z, and then this v, and this thing here is called gradient operator. This thing in the square bracket is called gradient operator, gradient, okay, and its symbol is just inverted triangle without any dot, without any cross, just this inverted triangle is for this. So, this minus here and this gradient operator here and v. So, this is a very general relation for electrostatic field, that is E is equal to minus gradient of v. Now, I have used Cartesian coordinates in spherical polar or cylindrical polar. You have different expressions, but nevertheless this vector relation is correct, that if you know this v for the given charge distribution, then using this gradient operation you can get this electric field. And how do we ensure that for every charge distribution we do have a v? If there is an electric field, I will find a v, so that this minus gradient v will be E. That is ensured by the fact that for electrostatic field, curl of E is 0, curl of E is 0, divergence of E is rho over epsilon naught, and curl of E is 0, and this curl of E is 0. This ensures that you can always write E as a negative grade or gradient of a scalar function. This minus I can always absorb in this v. So, gradient of a scalar function, if curl of a vector field is 0, then that vector field can always be written as a gradient of scalar function, that is mathematically guaranteed. That is the way these operators are defined, curl and gradient, this comes from simple mathematics. Okay. Now, the divergence and curl I am emphasizing because if you know the divergence of a vector field everywhere in the region of your interest, and if you know the curl of E everywhere in the region of interest, and at the boundaries you know what is this field, then you know everything about that field, that electric field. If you know at the boundary, and you know divergence everywhere inside the region of interest, you know curl of E inside that region of interest, and you know the values at the boundary, then everything about E is uniquely determined. That is why curl and divergence are so important. Now, for magnetic field, magnetostatics we are starting with, but it is valid for time varying magnetic field also. So, for magnetic field these equations are different. The divergence is 0, divergence of B is 0. Here the divergence of E is not 0, it is rho over epsilon naught. Wherever there is charge you have non-zero divergence, and curl is 0, and here curl is not 0, curl of B is mu naught J. Now, if I am writing this, it is magnetostatics. Steady currents. Magnetostatics means time independent current, not depending on time. Magnetic field not depending on time, electric field not depending on time, no change in the electric current density. So, curl of B is not 0, therefore, you cannot define, since this is non-zero, you cannot define a scalar magnetic potential. since curl of E was 0, we were able to define E as a gradient of V, and therefore, we could define this scalar electric potential V. But here curl of B is not 0 everywhere, and therefore, you cannot define a scalar magnetic potential, so that B equal to some minus gradient V type equations you cannot write. In some cases, in some limited regions where there is no current density and therefore, this J is 0, in those limited regions you can perhaps define a magnetic scalar potential and make use of the fact that curl is 0 there in that region, but universally no, if the curl is not 0, then the scalar potential cannot be defined. But then divergence of B is 0, just as this, if curl of E is 0, this ensures, this guarantees that a V can be found, scalar function V can be found so that E is gradient of that scalar function. This ensures. Now, this ensures, this divergence of B equal to 0. If the divergence of a vector field is 0 everywhere, then that ensures that a vector field, let me write it A, that is the standard symbol A vector field can be found so that this B is curl of A. Okay. So, if curl of a vector field is 0, that ensures that a scalar function can be found, so that you take the gradient and you get this electric field. And if the divergence is 0, divergence of a vector field is 0, that ensures that you can always find another vector field A, so that this B is curl of A. So, some kind of similarity and some kind of dissimilarity, and this A vector for which curl of A is the magnetic field is known as vector potential, magnetic vector potential. Okay. Now, the next thing is that is it unique? Is it unique if I have found a vector field capital A and I have checked that yes, curl of A is giving me the magnetic field? Is this the only vector function A, or there may be many such vector functions, so that each of them gives me curl of A is equal to B? So, if I again come to the electrostatic case and I say that okay, I have found a V, I have found a scalar potential V, and I have checked that negative gradient of V is electric field, I have checked that. Same question, is it the only one unique function, or there may be many such functions, so that minus of gradient V is same E? And you know that yes, there are infinite functions for any given field, but because the 0 of potential is your choice, 0 of potential you can choose anywhere, and therefore, if you have this V, so that gradient of V with a negative sign is giving you E, you can add any constant here, any constant you can add to this V, and if you take the gradient you will get the same E, right. because when you are taking gradient, you are doing del x, del y, del z. You are differentiating with respect to x, y, z, and constant differentiation gives you 0, and therefore, this is same as this. So, if you get one potential function, you can add any constant to that and you get different functions, and each one can be a valid potential for that electric field. Now, here the thing is more romantic. It turns out that if you, first thing is that curl of any gradient function is 0. So, curl of any gradient function is 0. This phi may be any function of x, y, z, r theta phi, s phi z. Curl of any gradient is 0, that will come from mathematics, no physics involved here. The way this gradient is defined, the way this curl is defined, this always happens. And therefore, if you have gotten A, so that B is equal to curl of A, you have gotten some function A, so that the magnetic field is curl of A, then you can always add any gradient function of this, not just constant. You can add any function which is gradient of a scalar, and this is scalar function, your choice, whatever you want you can choose for this phi as a function of x, y, z or s phi z or r theta phi, and then do this gradient operation, add that whole function into this A, and once again if you take the gradient of this will be equal to gradient of A and then plus 0, because curl of any gradient function is 0, and therefore, this is same as B. So, if this is a valid potential, this is also a valid potential, and you can choose this phi in infinite different ways, and therefore, you have a large number of functions. So, just like there in electrostatics case, we were given a choice that okay, you choose that, okay, fine, at this point the potential will be 0 by definition. Here also we have a choice which A to be chosen, and the choice we generally take is we demand, just like there we demand the potential should be 0 at this point of my choice. Here we demand that your vector potential should be such that divergence of that A vector is 0 by choice, no physics. You take 0 potential in electrostatic case here or there, no physics involved, it's just a choice, I take the 0 here or I take the 0 there. Similarly, here it is just by choice that we choose A such that divergence of A is 0, and then comes another beautiful pair of equations, and let me write it here. Divergence of A is 0. Divergence of A is 0, my choice, and curl of A is B, definition, and compare this pair of equations and this pair of equations, identical mathematical structure. Divergence is 0 and curl is not 0, some function. Divergence is 0 and curl is not 0, some function. So, we will exploit this symmetry. We know many of the results, this kind of J will produce this kind of B. So, using those symmetries, we will be finding if this is the magnetic field, this will be the magnetic vector potential, and so on. We can do all those things. Now, next. So, can I directly write the function A once the current distribution is given? Actually, that is the goal. For finding magnetic field, if I am trying to get A and then taking curl of that A, I am trying to get this B, then I should be able to write that A first from the current distribution. So, how is that related? For that we will be doing some algebra. I will state many things without going into just calculations, algebraic calculation, that does not make much of sense. Take this as equation, start from here. Curl of B is mu naught times J, and that means curl of A is equal to mu naught times J. Okay, B is curl of A, so B is the curl of A. So, I am writing this B as curl of A. Now, curl of a vector. First you take a curl, you get a vector function. This A itself is a vector function, and then you take curl, you again get a vector function, and for that vector function you again do this curl operation. So, that is curl of A, and that turns out to be gradient of divergence of A. This I am writing without proving, and this is, and minus del square of A, that is the expression for this quantity. That is the expression for this quantity, and this should be equal to mu naught times J. So, what are these things? A is a given vector function, and for a vector function you can do this divergence operation. We have talked about divergence, we have expressions in Cartesian coordinates, spherical polar coordinates, cylindrical polar coordinates. So, you can do this divergence of A. You will get a scalar function as a function of x, y, z. Everything is function of space point. So, this scalar function is there, and then do this gradient operation. For gradient also you have expressions for Cartesian coordinates I have written, and similarly for cylindrical, polar and spherical. So, do that, again you get a vector function, and on this side this operator del square is written. This del square is called Laplacian, and if you are using Cartesian coordinates, it is just del square del 2 del square and plus del 2 del y square and plus del 2 del z square, and generally operated on a scalar function. So, we write del square of phi is equal to del square phi del x square plus del 2 phi del y square plus del 2 phi del z square. So, that is the meaning of this operation. So, if I take x component of this let us write only, this is a vector, this whole thing is a vector function, this is a vector function. So, if I write the x component of it, it will be divergence of A is 0. Divergence of A is 0, that is our choice, and therefore, this term goes away, and you get minus of del square of A x. We are writing only the x component. So, this is equal to mu naught times J x. Okay. So, del square of this A x is equal to minus mu naught times and then this J of x. Now, this equation is also a very famous equation for electrostatics, very famous equation for electrostatics. Let me quickly tell why is this famous and what the meaning of this equation in electrostatics. Okay. For electrostatics, E is written as minus gradient of the potential function, and if you write divergence of E, that is equal to minus rho over epsilon naught. Rho is itself a function of space point. You have charge distribution. So, at different points you have different charge density. So, this is a scalar function of a space point, and for this E, if you write here minus of gradient V, this is divergence of E is rho over epsilon naught. So, this divergence of minus gradient V is rho over epsilon naught, and this is now minus divergence of gradient, and divergence of gradient is your del square. Divergence of gradient is your del square, and then you will have minus del square V is equal to rho by epsilon naught, or del square V is minus rho over epsilon naught. Now, this equation which connects potential, electric potential, with charge density, and this equation for magnetic vector potential and the current density, you can see they have identical structure. This is known as Laplace's equation. Not only for electrostatics and this vector potential here, this Laplacian equation is used in many other branches, in heat transfer, in many other branches, the same mathematical structure. Del square of V is a known function of rho x y z. Here this del square Ax is known function current density Jx, identical structure. So, whatever is the solution here, that same will be the solution here, and you know the solution. If you have a charge density, charge distribution, you have a charge distribution in this, say in this volume, and rho is a function of space point. You have all x, y, z axis, and then this, and then you want potential here. How do you write that potential at P? If you take a small part here, some d tau, and the charge here is rho times d tau, and rho where at this, let us say r prime, this vector is r prime, our standard way of writing. So, this is your charge, and then divided by 4 pi epsilon naught, and then r minus r prime. This distance divide by this distance, this is your r minus r prime, this is r. So, that is how you write the potential. Potential due to this is this charge divided by 4 pi epsilon naught, distance from the charge to the field point, that you write here, and then integrate. So, V is equal to this, that is the potential here, and that is the solution of this equation, because the potential has to satisfy this fundamental rules. So, this equation gives you this solution, all right, and therefore, this equation here you have epsilon naught in the denominator, and here mu naught is in the numerator. So, that taking that into account, we can write this Ax is equal to, from here I am writing from here, rho r. Where is rho? Rho is here, and here we have Jx. So, it is Jx d tau. 4 pi here, this is in denominator, we will have mu naught in the numerator, because in the basic equation it is here epsilon naught in numerator, and here it is numerator. So, you will have mu naught here and 4 pi here. So, 1 by 4 pi epsilon naught is replaced by mu naught by 4 pi, and then it is just that r minus r prime. Okay. So, this will be the expression for A x. And how does this figure translate? This figure translate identically. What I have is a volume, and in that volume there are some currents somewhere, and the current is described by current density J at this R. And because of this current distribution, we are trying to write the vector potential here at P, and then we take some volume, and how much is the current there. So, that current element J d tau, because of that, what is the vector potential A x there, and then you integrate over the entire thing and get the total vector potential. Same description. You have a charge distribution, you take a small volume here, see how much is charge here. You have a current distribution, you take a small volume, see how much current is there, J d tau, how much is charge here, rho d tau, how much is current here, J d tau. Then because of this, write the potential here. So, because of this, write the potential here. And how do I write the potential here? Rho d tau, J d tau, 1 by 4 pi epsilon naught, mu naught by 4 pi, r minus r prime, the distance, divide by distance, yes, divide by distance. So, that is how you get A x, and similarly A y, and similarly A z. So, if I combine all these three, can I write an expression? Your A x is mu naught by 4 pi J d tau integration. Did I write integration? No. Yeah, integration. This integration here. So, integration of this, and then r minus r prime j x. This is j x. This is A x. What is A y? What is A y? A y will be integration mu naught 4 pi j y d tau. Current density itself is a vector, remember. And then we will have r and minus r prime like this, and Az will be integration mu naught 4 pi jz, and then d tau, and by r minus r prime. Combine all these things, I cap times this, j cap times this, k cap times this, and add this side, you get vector A, and that is equal to integration, this mu naught by 4 pi will be everywhere. So, mu naught by 4 pi, whether it is x component or y component of z component of A, r minus r prime modulus, it is here, it is here, it is here, that is also common. So, r minus r prime, this is distance from the element. So, this we have written, this we have written, this we have written, d tau is here, d tau is here, d tau is here. So, it is d tau. Then I cap jx plus j cap jy plus k cap jz, I cap jx plus j cap jy plus k cap jz. So, it is just j vector. It is just j vector. So, that is a general expressions. If the current density is known, I can write the vector potential using this. And this is in terms of volume current distribution that I have written, but if you have linear current or you have surface current, you know what to do. Just replace this j d tau, this j d tau. If it is a linear current, j vector d tau is replaced by I dl vector. That is the current element for linear current. And if it is surface current, then this J d tau will be replaced by k dA. If it is a surface current distribution that is given to you, you can write the vector potential this way, J d tau replaced by k dA. If it is linear current distribution, then you write it this way, J d tau is replaced by ideal. So, that is how you can obtain the magnetic vector potential if the current distribution is known.